Welcome to the next exciting edition of Chapter 5, Number 3 in the Real Number Systems. This is 5.6, Exponents in Scientific Notation. In this section, we're going to use properties of exponents and then convert them to scientific notation, to decimal notation, convert decimal notation to scientific notation, and then perform computations using scientific notation and solve problems using scientific notation. All right, let's jump into it. So the product rule for exponents, b times b to the m times b to the n is the same thing as adding the exponents. So an example over here, 9 to the 6th times 9 to the 12th is the same thing as 9 to the 6 plus 12, or 9 to the 18th. The product rule, so when you multiply like bases, you add the exponents. Here, the power rule is when you raise an exponent to another exponent, you multiply them. And then the quotient rule, when you have b to the m and b to the n and they're dividing, then it's the same thing as subtracting. Notice here that it's always the top minus the bottom. Okay, so the top exponent minus the bottom exponent. And also notice that all of these, you have a single base, right? So this isn't like 3 and 2. The bases here are the same. They're both the base b. All right, so that's an important connection to make as well. Let's see. What else is happening here? The zero rule. So the number or an exponent of 0 means that the value of that base being raised to the 0 exponent is itself 1. And I think you can kind of, it's not a proof, but one way to kind of think about it is, let's look at like 2 to the 3rd. Okay. And then 2 to the 2nd. And then 2 to the 1st. And then 2 to the 0. And then 2 to the -1. To the -2. So if we kind of look at the pattern that's happening here, this is like 2 times 2 times 2. This is like 2 times 2. This is like 2. Okay. And so what is this like? Well, this, if you think about it, this is 3 2s, 2 2s, 1 2. It can't be 0 2s, or we'd write 0 2s would be, there's a 1 there. Okay, and then here you're going to get 1 over 2, and then you get 1 over 2 squared, or 1 over 2 times 2. And then you have 2 to the -3. That's equal to 1 over 2 times 2 times 2. Okay. So if you're looking at the pattern of increasing and decreasing exponents, it should make sense then that 2 to the 0 power is the case when you get just a single value of 1 there. All right. Using the 0 exponent, so 7 to the 0, pi to the 0, all of these values are 1. This one is -1 because, again, it's the base here is 5. And so 5 to the 0 is 1, and there's a -1 out in front. Okay. The negative exponent, as I just showed earlier, the negative exponent just means that doesn't mean that the base is negative. It means that you're thinking of it as bringing it downstairs to make it positive. So that's like 1 over that number. All right, and so how is this helpful? Well, it allows us to write things in a neat way, and also helps us to simplify things, especially when numbers get really big or exponents get really large. So 7 to the -1 is 1 over 7, or to the first power, just 1 over 7. Usually we don't write the exponent if it's a 1. Here we have 1 over 8 squared, bringing it downstairs. That means 8 times 8, which is, of course, 64. And same thing here. 5 to the -3 is 1 over 5 cubed. 5 cubed means 5 times 5 times 5, so it's 1 over 125. Right. So that exponent rule, and why we're talking about it there, is because we're going to use that with powers of 10. The nice thing about powers of 10 is that the number here will tell you how many zeros you have as a shortcut. And why is that? That's because when you have 10, let's say, raised to the 10th power, right? So 10 squared is equal to 10 times 10, which is 100. So if we go back to what we talked about in, it was 2 lessons ago, this is how many of these you have. And so we have 10 groups of 10. And so we have 10 tens here. And if we did, let's say like 1,000, so 10 cubed, that's like 10 times 10 times 10. Now, if I use the associative power of, or rule of real numbers, so I've already done this one. This is 100. That's what we just did. And so this is saying that I have 10 copies of 100. 10 copies of 100 is 1,000. And so you can see then that we have 3 zeros corresponding to the exponent here. We have 2 zeros corresponding to the exponent here. And so this pattern continues even with negative exponents. The difference is, if you notice here, I'm moving over 1, 2, 3, 4, 5, 6, 7, 8, 9. And so that's why it's a negative 9, is that I can express this as 1.0 times 10 to the negative 9th. And this would be scientific notation here, where the exponent tells you which direction to move the decimal. And then it also tells you something really fundamental about why we would use scientific notation, is because this number is really small. That's on the order of 10 times the size of an atom. Okay, so an atom would be 10 to the 10th, negative 10th, or an angstrom. And this is on the order of a nanometer, which is the wavelengths of light. So visible light is like, let's say, 700 nanometers. So that is on the order of visible light spectrum. So you can tell how small that is, because we don't even see the waves of light in terms of waves, right? So the wavelength of light, lambda, is on the order of a nanometer, 10 to the minus 9th, which is what this length is. Okay. All right. So let's explore this a little bit. So a positive number is written in scientific notation, can be expressed in the form A, the base, not the base, the numerical value, times 10 to the n, where n is an integer, just like in the previous example, we saw it was negative 9. If n is positive, then you move it in places to the right. If n is negative, then you move it in places to the left. All right, so converting then is a matter of moving it left or right. And so, and just like in these examples here, you see, in this case, since the value here is 10 to the 10th, this is a very big number, so we're going to move it to the right, it being the decimal point. And in this case, this is a very small number, so we're going to be moving the decimal place to the left. And so this is 0.00011. The number of places you move the decimal corresponds to the number of the exponent here. Converting from decimal to scientific notation then is just a matter of knowing what direction and counting. So if you're moving it to the right, you're going to have a positive number. And if you're moving it to the left, it's going to be a negative number. So undoing that, you're going to be moving this to the left to right in this direction. It means you're going to have a positive number. Okay. All right, so let's look at that. So here, I put a decimal here, and I'm going to move it 1, 2, 3, 4, 5, 6. So this is going to equal 4.6 times 10 to the 6th. Likewise here, I'm going to move it 1, 2, 3, 4, 5. 1, 2. Oh, you got something. Let me erase that and start over. Let's start again. So I have 1, 2, 3, 4, 5. So this is going to equal 2.3 times 10 to the negative 5. All right. Hey, we did it right. Okay. Computations with scientific notation. So just like we did before, using the rules of exponents, whenever you are multiplying, you're going to multiply your two digits, a and b. And then since we have like bases with the exponents, we're going to add m and n together. So you have a times b, and then you're going to multiply it by adding the exponents together here. Okay, so for example, if we have 3.4 times 2, then you multiply 3.4 times 2, and then you add 9 and -5. So that should give you 4, and then 3.4 times 2 is 6.8. And so you get 6.8 times 10 to the fourth, which is 68,000. Okay. Dividing is exactly the same thing. You divide a by b, and then just like before, we're going to take the top exponent and subtract it from the bottom. I think I said that unclearly or incorrectly. We're going to take the exponent on the top and subtract the bottom exponent from it. And so here's an example of that. We have 8.4 times 10 to the -7th divided by 4 times 10 to the -4th. So here we're dividing the values, and then here we're going to subtract -7 and -4. A negative and a negative, we're going to 4 to -7. We get 2.1 times 10 to the -3rd. And so if we move the exponent, by the exponent we would move it 3 to the left. And this will become 0.0021. All right. So scientific notation is used for numbers that are really, really big or really, really small. And so in this example, the national debt is a very huge number. And so we're going to use scientific notation to notate that. In January 2016, the national debt was 18.9 trillion, or 18.9 times 10 to the $12. At that time, the US population was approximately 322 million, or 3.22 times 10 to the 8th. If the national debt was evenly divided among all the individuals in the United States, how much would it have? Would each citizen have to pay? So this is talking about equal groups of. And so in this case, then the amount each citizen would have to pay is 18.9 times 10 to the 12th divided by 3.22 times 10 to the 8th. So just like we would do before, we have 18.9 divided by 3.22. Subtracting exponents, then we'd have 12 minus 8. And so this is saying that each one of us would owe, in that situation, $58,700. Okay. All right. Well, I hope that was helpful, and I'll see you in the next video.